So we'll start. It's 5. So good evening everybody. Welcome to the second day of our webinar series on contemporary topics on nuclear physics. And of course, good morning to the first speaker and good afternoon to Professor Marco. And let me introduce a bit for today's first speaker. First speaker is Professor Valdir Guimarães from University of de Sao Paulo, Brazil. He has become a graduate in physics from University of Sao Paulo in 1984. He has done his master's from the same university in 1988 and PhD from the same university again in 1994, and presently he is an associate professor at the same university. He is working in the field of nuclear physics, focusing on nuclear reactions and scattering. His research areas include the topics like elastic scattering, transfer, breakup, fusion and fission reactions, spectroscopic investigation of light exotic nuclei rich in protons or in neutrons, study of nuclear reactions of interest to nuclear astrophysics or some other areas. A very good friend of Dr. B.K. Nayak, who also visited BRC some time back. No sooner we contacted him, he immediately accepted our invitation to speak in the present webinar series. So today he will speak on the topic dynamic and static effects in elastic scattering of light exotic nuclei. So I request now Professor Valdir Guimarães to start his presentation.
Okay, well, thank you for the like the thanks for the opportunity to talk to this event, and also congratulate Nayak for his birthday. And we met in 2009. He was playing with some relative IUP also from India. So we will talk more or less about some of this related work. Yeah. And I will start the presentation. So the idea of this talk is talk about some elastic experiments and see some dynamic stability effects. And the idea is light nuclei. Usually they have a strong cluster structure, like C6 or PN8, 8 and 11 are the famous one, but also some other like Iridium 9, Iridium 10, Carbon 10, they have some alpha cluster combined with some proton or neutron cluster configuration with some of them like this molecular orbital cluster structure. So they have some interesting structure, and this structure somehow interfere or has some correlation with elastic scattering. That's what we are going to see in this talk. So first of all, the famous Halley structure for lithium-11. So lithium-11 has these two neutrons loosely bound to a core. So if you can see here, we start to see lithium-7, lithium-9, but for lithium-11, you have these two extra neutrons orbiting a core, and by the end, the size of this circle is almost like a LED. And also you have this Borromean structure. The Borromean names came from this combination of the rings. So these three rings are collect, and if you break one of them, the other two will also go apart. And this came from the Borromean family in Italy, but also there's a lot of Japanese family also with the same letters. The idea for the nucleus is you have a core and the two neutrons weakly bound, and if you take one of these one also goes apart. So this kind of nucleus is called borromeo nuclei, and the lithium 11 is one of them. Helium 6 is the other, and helium 8. So you can see for the helium 6, you have a helium 4 core plus 2 neutrons with a very low binding energy. For lithium 11 is this. And in case you take one of the neutrons, so you leave with helium 5, and helium 5 is not bound, and also breaks up in 4 plus neutrons. So it means if you take one neutron, the other one also goes apart. There are many of these nucleus with interesting structure, like if you see this chart, you see the stable nuclei and the radioactive neutron rich, and the other side is the proton rich. So some of them have one proton halo or two proton halo, one neutron halo or two neutron halo, and they are here. So these nuclei are the most interesting to be investigated because they have this exotic structure. And from the proton-rich side, you have the boron 8, carbon 10, nitrogen 12, fluorine 17, and the neon 17. So these are the most interesting ones because they have this kind of one proton halo or two proton halo configuration. And some of these properties for these exotic nuclei are first, they have some extended matter distribution. So like boron 8, they have extended matter distribution. It means this proton, these valence protons, orbit is in a core with some extension in the matter distribution. For the lithium 11 is the most famous case. So this distribution goes pretty far from the core. So here's the size of the nucleus. And also the neutron distribution. If you see the stable nucleus, when you put protons and neutrons, they distribute like this in the potential. So to take one of these neutrons or take one of these protons, the separation energy is more or less about 10 MeV. But then when you go to neutron-rich or proton-rich nucleus, so for the neutron-rich, you have a weakly bound neutron, which means to take one of these neutrons is very easy, so the binding energy is very small. But if you want to take one proton, it would be very difficult. So the binding energy for the proton is pretty high. So we have a imbalance of the neutron and proton binding. Some other weakly bound or exotic nuclei are here. So you have a list. For instance, boron 8 is bound, this proton is bound by only 137 keV. For the helium 6, the 2 neutrons is bound only for this. So for this exotic nuclei, the binding energy for this valence 1 neutron or 1 proton is very low, below 1.5 MeV. This other, we can call weakly bound nuclei, since the binding energy is between 1.5 and 3 or 4 MeV, so they're considered weakly bound. Of course, the frontier between being weakly bound and tightly bound is not so clear, so some of them can be considered weakly bound or tightly bound. It depends on the binding energy, but the frontier is not so clear. But it's clear that if you have more or less 2 MeV or 3 MeV, they are called weakly bound. And for these, like oxygen 16 or boron 11, the binding energy is pretty high. The other interesting property for this exotic nuclei is the structure or this magic number changes when you put too many neutrons or too many protons. So for instance, the normal and the ordinary nucleus has this magic number 2, 80, 20, 29, and 50. But when you go to exotic nuclei, these shell magicity start melting. So these levels or these orbits is starting to change or moving here. So we call that we have a kind of a melting of shell magicity, and new magic numbers may appear, and sometimes you have a spin inversion for the ground state, for instance. One example is here. So you see the very clear definition for the magic number is when you go to the first excited state, if the energy is too high, it means you are going from one shell to another shell. So for oxygen 16, you have a very high excitation energy for the first excited state. So we say that this is a magic number, and 20 is a magic number, and 28 is a magic number for neutrons. So neutron magic number, neutron magic number. But when you go to exotic nuclei like helium-6 or oxygen-24, you also get a very high energy for the first excited state, meaning you have a new shell model or new magic number. So you have here a new magic number like n equals 6 or n equals 16. So these are some characteristics, static characteristics for these exotic nuclei, but they also have some dynamic effects or dynamic characteristics. And this related, for instance, in the elastic scattering. For these exotic nuclei, we have somehow a strong absorption in the elastic scattering, meaning that the angular distribution shows some kind of a smooth angular dependence and total or partial absence of this Fresnel diffraction. This Fresnel comes when you have a hard sphere, for instance. You have a scattering of two hard spheres. This Fresnel peak is just an optical effect, and it's very clear when you have an ordinary nuclei. But when you have exotic weakly bound valence particle in exotic nuclei, you have an absence or complete dumping of this Fresnel peak in the elastic scattering. And so also, the cross-section starts to deviate from the Rutherford equation in a very small angle. So usually for ordinary nucleus, you have the cross-section for the elastic scattering divided by Rutherford, like 1, 1, 1. But for this exotic nuclei, it's starting getting below 1 very early, which means it's starting to deviate from Rutherford in a very small angles. And this is influence of this long-range absorption, which suggests the presence of some reaction mechanism that remove flux from the elastic scattering at distance beyond the strong absorption ranges, like polypolarization or quadrupolarization. So it means that this valence particle in the exotic nuclei may induce some other reaction mechanism like breakup, and I will discuss a little bit further about this. And then this breakup has influence in this elastic scattering exactly by removing this Fresnel peak. So I can show here the two cases for this dumping of Fresnel peak for boron 8 and beryllium 11. These two nucleus, they are boron 8 nucleus and beryllium 11 nucleus. This is a proton-rich and this is a neutron-rich nuclei. And you can see for high energy, you have a very clear this Fresnel peak, but as you go to close to the barrier, boron 8 lead, boron 8 on lead, here is above the barrier, here is above the barrier. So you can see the dumping of the Fresnel peak. For zinc target, so here is well above the barrier, and here is close to the barrier. So when you have close to the barrier, you have this dumping of the Fresnel peak. But for you see, you can clearly see when you have a heavier target, like lead target, this dumping is very strong. For beryllium 11, which is a neutron exotic nuclei, so here is beryllium 11 on lead, so it's a very strong dumping on the Fresnel peak, where the energy even higher than Coulomb barrier, and this is for the energy close to the barrier, so the dumping is quite strong. We have data here. This data is already published. We have data here, but it would be interesting to have data in some other region, like this one here. It was just published last year, an experiment by Mazoko, performed in Riken in Japan. So the angular distribution shows exactly a very clear damping of this Fresnel peak, which is a clear indication of the Halley structure for the boron 8. We also just finished one work about this beryllium 11 on lead. I don't have the data here. We just submitted to Physics Letters B. But I can assure you that there were a strong dumping of this Fresnel peak. So moving further, so why you do elastic scattering measurement? So the discovery of this exotic nuclei renews somehow the interest in the investigation and modeling nuclear reaction, and in particular also the elastic scattering. First, because elastic scattering is a peripheral process, and we can learn about the surface property of the projectile by getting some experimental data on this elastic scattering. And the elastic scattering is also useful to investigate this static effect like this halo and bromine structure of exotic nuclei, but also to investigate correlation and couplings between reaction channel and elastic scattering, which we call dynamic effect. And this peculiar structure of the exotic nuclei should affect the reaction mechanism like breakup, it will affect the fusion and the elastic scattering mechanism. And in these days, we have some relative intense beams in most of the laboratories. So most of the laboratories are somehow trying to improve as much as possible the beam intensity for these radioactive ion beams. So we can now do some very nice measurements using these radioactive ion beams. I have here a review. It's already getting old, so it was published in 2016, but it's still a very interesting review showing all this experiment with a radioactive beam like elastic scattering, fusion, breakup of light exotic nuclei in this 10 years range. But I just finished a new review on total reaction cross-section, and in this review we show some important characteristic for this elastic scattering experiment at the low energy regime. So we just finished writing last week, and we are about to submit it to European Journal of Physics. Well, to investigate elastic scattering, what we do, usually we get angular distribution measured at different energies. In particular, it's interesting to measure the energy close, below or a little above the Coulomb barrier. And for the analysis, we can do all kinds of analysis. We can do some conventional optomode analysis using Wood-Saxon potential, or some potential called double folding potential, like the São Paulo potential. And in this potential analysis, we can also improve and do some short range, long range potentials. But also we can do cluster model, CDCC calculation, couplet channels like inelastic transfer, and also the CDCC breakup calculation for the analysis. And the important is to get some physics. So we can take the physics considering the threshold or breakup threshold anomaly investigation, or results from the couplet channel calculation, interaction distance, total reaction cross-section with appropriate reduction. In this talk, I will focus more about the results from the couplet channel calculation I have been working with. So for this, I performed some experiments in different places, like helium-6 and boron-12 on nickel at the University of São Paulo, using our double solenoid system to produce these helium-6 and boron-12 radioactive nuclei. And also at Notre Dame with boron-8 and carbon-10 on nickel, and at Argentina with a stable boron-10 and boron-11, and also recently at Texas A&M, this carbon-10 on lead. So I will talk about these experiments. So first, the way we do this couplet channel calculation is like this. So usually you have the potential, the short range potential in the potential analysis is to take care of the fusion. So when the particle tuning the barrier, you have the fusion. But to investigate or to take into account the direct reaction, we have to use some long range potential. But however, when we do the couplet channel calculation, we keep the real potential. For instance, this double folding potential is one of I used. But for the imaginary potential, I replaced by couplet channel. Using the polarization potential, I will consider directly the coupling to the channel. So fusion, since the fusion is not considered in this couplet channel, I have to take care of the fusion considering a short range potential. So I keep this short range potential, but if I want to see the effect of the other reaction, I treat this other reaction in the couplet channel. Sorry? So I replace the imaginary potential by this couplet channel calculation. Okay? So this short range potential was discussed, these particular parameters was discussed in this paper here to show that this parameter is quite reasonable to consider as the short range to take care of the absorption, to take care of the fusion. So what I have to concentrate is in this part, which channel should I consider to do the copper channel analysis? So I can consider the inelastic by considering the formation, like a quadrupole deformation, a rotational or vibrational model in the copper channel. But also, if the transfer is an important channel, I have to perform the CRC calculation, where I explicitly take into account this transfer reaction. But in case about the nucleus, I have to take care of this possible excitation to the continuum through this CDCC calculation. It's a continued discretized copper channel calculation. And this is the way we take the breakup into account. Important is, if all the channels are taken correctly or our effectors are correctly considered, no imaginary potential is needed. So we also just add this copper channel, and I have to describe the elastic scattering without the including any imaginary potential, at least any surface imaginary potential, because as I said, I still have to keep the short range for the absorption. All these calculations were performed with the code Fresco. So for the breakup is particularly important because this low binding energy can have some excitation to the continuum. So how do we treat the continuum in the copper channel analysis is by discretize this continuum. So we do a discretization of this continuum and considering all this coupling to all these PCL states. So the breakup is particularly important for this weakly bound nuclei, and we include it in the copper channel calculation by considering this discretization. So this is called the CDCC continuous discretization copper channel, and it has to be associated with a cluster model. So if we perform this discretization, we have to consider which breakup is there. So we can have to have this breakup, we have to consider a cluster model for the nucleus. And this can be 3-body or 4-body or 4-body cluster model, and I will explain it a little bit later. So the idea is, in case we have this Borromean nucleus, it has a core and the 2 neutrons, we can either consider it as a d neutron. So we have a 3-body interaction. So we have this cluster here, the core, and the target. So we call this 3-body, 1, 2, 3. And we need actually these 2 potential, but this, or I consider these 2 neutrons as independent. And then in this case, I have the 4-body interaction, which corresponds to this neutron, the core, and the target. Just to give an idea of the importance of this 3-body or 4-body treatment for this cluster configuration, I have here the data for helium-6 on lead. So this is the data, and this is the calculation without any coupling to the continuum. But if I consider the 3-body, I have this green line, and if I have the 4-body, I have the right description of the data. So it's very clear the importance of this 3-body interaction, which is considered the d neutron in the helium-6. So helium-6 can be described as helium-4 plus a d neutron, or helium-4 plus neutron. So this is important. The 4 CDCC is important to describe the data. Anyway, first experiment I performed some years ago in Notre Dame, boron 8 on nickel. So we used the boron 8 radioactive ion beam. So this boron 8 was produced by this twin source facility at Notre Dame, which consists of the 2 solenoids. So I will show how is the working principle of these 2 solenoids, but the idea is this solenoid can select a particular beam, in the case boron 8, but in this particular case, I could not separate the lithium 6, beryllium 7, and boron 8. So I have the 3 beams together. It's like a cocktail of beams that all 3 together. But if you want to do some elastic scattering, I can clearly separate them. So it's like to have an experiment with 3 beams at once. So for this, we performed at the same time 3 beams elastic scattering in different energies. But let me put some parentheses here and explain to you how this solenoid system works. So the principle works is like this. We have here a primary beam, production target, and we have the two solenoids, and here's the reaction chamber here or here. And the idea is the following. So the solenoid, you have here the production target. So let's say I have a primary beam as a lithium 7 on a deuteron target, and we produce all these kind of nuclei. Lithium 8, lithium 7, helium 6, helium 4, and let's say I want to select the lithium 8. So what I do is I adjust the solenoid to focus on the lithium 8 into the chamber or into the target, okay? And then all the others have different B roles. So all the other nuclei have a different combination of mass and energy produced in different B row, so they are focusing in different points, or before or after. And if I put this block and this collimator, I can block them and let only the nucleus I have interest to go through this combination of block and collimators. So that's the working principle of the solenoid. So it's by focusing the beam of interest. If I want lithium 8, it's just a question of adjust the current of the solenoid for the lithium 8 to be focusing here. So this is a picture of the solenoid system. So you have the two solenoid here, and here is the production target. And this is the one installed in São Paulo. So we have a very similar system. So we have the two solenoids, and here is the production target. And in principle, as I remember, NIAC wants to install some similar system at the BRC some years ago. I don't know how the project is going now, but it's an interesting idea to produce this light radioactive ion beam. And here is a list of the beams we have been working on for a few years now. So we have a helium 6, lithium 8, beryllium 9, and here I list those produced at Notre Dame and São Paulo. So Notre Dame has doing some more producing some different beams like carbon 10, nitrogen 12, but also we have oxygen 13 and oxygen 14. So we have all these kind of light nuclei. We can produce beams, and this is more or less the intensity. So the intensity is 10 to the 6 particle per second, 10 to the 50, which is enough to do some elastic scattering experiment, some resonance scattering experiment, or even some transfer reactions. And of course, this intensity is based on the primary beam intensity of about 1 microamp beam, which is usually the primary beams lithium 7, lithium 6, boron, and carbon, which is possible to get 1 micro primary beam. So back to the boron 8 nickel elastic scattering. So these are the results. So we have the angular distribution divided by Rutherford for several energies, 20, 23, 25, 27, 29. So as you can see from this calculation, this is the breakup plus inelastic, but no coupling to the continuum, and the blue line is just the elastic scattering with no coupling, the red line here. So to describe the data, what we need is a combination of inelastic and all couplings, including the continuum, including the breakup CDCC calculation. So it means that for boron 8, which can break up in beryllium 7 plus proton and has this 2 plus spin. So the three-body, we can consider the three-body CDCC calculation, where you have the boron 8 breaking up in beryllium 7 plus proton to the continuum. And what I can say is that the important channel to describe this elastic scattering is the breakup and the inelastic, the breakup being very important. So CDCC breakup and the copper channel elastics are the important channel to describe this elastic scattering. For the helium 6 on nickel, so helium 6 is also bromine, azotic, and nuclear. So we performed some elastic scattering measurement in 3 different energies. And again, the CDCC was very important, but also what was very important was the four-body description of the helium-6. So we can see the blue line and the red line. So the blue line is the three-body, and the red line is the four-body CDCC calculation. So clearly the data is better described by the three-body CDCC. Also, it's important to say that the elastic flux removed from the forward angle and it's bring it to the back angle. So the idea is you dumping the Fresnel peak and there's a rise in the cross section at back angle. So this is a clear characteristic of a strong absorption, and in this case, this strong absorption is due to this breakup of these two neutrons. For the stable beryllium 11 on nickel, so I also performed this experiment in Argentina, and for boron 11, I just want to do this measurement to be a counterpoint or to compare with the boron 8, because boron 8 is a weakly bound, and the boron 11 is a strongly bound nucleus, so the binding energy is pretty high. And also it is well deformed the nucleus. So breakup is not important channel because this binding energy is too high. So the spin is a small spin, so spin orbited by may not be important, and transfer is not important because of this also this binding strong or high binding energy. So what the important is the inelastic and some reorientation. This reorientation effect is the spin projection. Now, since you have some deformation, you need to consider the spin project in the rotation x, which is proportional to the quadrupole moment. So if you take this reorientation and this inelastic, we could describe very well this experimental data. So you can clearly see that the reorientation and couplings to the inelastic scattering is very important to describe the data. But what I can say is for this particular nucleus, breakup, spin order, and transfer is not important. What is the main channel, the most important channel is the inelastic channel. But also have data for boron 10. Boron 10 has a large spin and also quite deformed, but the binding energy is also high, so breakup might not be important. So we investigate all the other factors, and the transfer, we performed some CRC calculation, the elastic scattering, and the factor for this transfer is very small. But however, when you do the inelastic couplings and the spin orbits, we could describe the experimental data. So it means these two effects are important effects. In particular, the spin orbit is important because the ground state spin for boron 10 is quite high, it's a 3+. So since I performed the experiment on boron 8, boron 10, and boron 11, we've also performed it to do some systematic study in this boron isotope, the boron 12 on nickel at the University of São Paulo. So the boron 12 is a weakly bound. So we performed this experiment in São Paulo, also using this two solenoid system at São Paulo. So here is the spectrum delta E. So we have the particle identification spectrum, so we can clearly see the boron 12 here, well separate from the other. Of course, since we use only one solenoid, we have several contaminations, so the beam becomes like a cocktail at the beam. But since we have performed the elastic scattering, we can easily separate the boron 12 from the others. So we could identify and get the angular distribution only for the boron 12. Again, the breakup is not important because this is a kind of still high energy or high bind energy, so it might not be important. Also, the spin orbit might not be important because it's a small spin, the ground state. The quadrupole is also small, so spin orbit reorientation and breakup it might not be important channel. So what we did was consider the inelastic. You can see here, I also tried the spin orbit and the reorientation, but the effect is very small. So what the important is some the coupled channel. The inelastic channel was the important channel, and also the transfer. So this neutron transfer, the Q value for the neutron transfer is a positive Q value. So it transfer might be important channel. So we perform the CRC calculation, consider all this possible transfer, all this possible Newton transfer. And by consider the Newton transfer, we could describe the elastic scattering data. So in the coupled channel, we perform the CRC, and only after we do the CRC calculation, we could describe the experimental data. So it means that for this boron, the important channel is the transfer channel. So by putting this in a table, you have here the boron isotope, boron 8, 10, 11, and 12, and you can clearly see that depends on the configuration, you have a different effect in the elastic scattering. Like for boron 8, we have a low binding energy, and this is the important effect by the breakup channel. For boron 10, what the important effect is doing to the spin. So the spin orbit and the reorientation was a stronger effect in this elastic scattering. For boron 11, which is also well deformed, so the reorientation was the important channel. And for boron 12, due to this cluster configuration, the transfer was the important channel. So it's very clear that for the same nucleus boron, depend on the configuration for these isotopes, like different configuration, proton, halo, or the neutron, or the alpha structure, they have a different effect in the angular distribution. But also, carbon-10 is also very interesting nucleus to investigate. So carbon-10 is a proton-rich nucleus and has a very large deformation, which I would expect a strong absorption. But the interesting point for this carbon-10 is that it is a Brownian nucleus. What is a Brownian nucleus? It's a super-Borromean nucleus. Instead of 3 rings, like the Borromean nucleus, it can be described by 4 rings. So they're all 4 rings connected, and if you break one, all the other 3 also goes apart. It's like this. Carbon-10 has an alpha-alpha proton-proton configuration, and if you take one proton, all these 3 goes apart. If you take one neutron, all the other, one alpha, sorry, all the other 3 goes apart. So it's like this. If you take one proton, what we get is a boron 8 plus proton, but the boron 8 is also unbound, and it breaks up into alpha plus proton. If you take one alpha, what you leave is a beryllium 6, and beryllium 6 is also unbound, and it breaks up in alpha plus proton plus proton. So wherever you take, the other 3 also goes apart. So it's like an interesting nucleus because of this kind of configuration, and in particular, this cluster configuration. Of course, we are schematically drawing like an alpha proton, but it can be in a different configuration. It can be like this configuration, we are not sure. People are performing calculations to see how is the matter distribution, proton distribution, neutron distribution for carbon-10, to see how would be this configuration. But in my case, what I'm doing is the elastic scattering to see what would be the effect of this configuration in the elastic scattering. So I performed this experiment at Notre Dame. So the carbon-10 on nickel. So this experiment, we can usually identify, is again a cocktail of beam, but we can easily identify the carbon-10. So we measure one angular distribution. So it was a very difficult experiment, so that's why we got only few points. But we can perform some discussion. We can see, for example, what's the influence of the first excited state of carbon-10, and we could see a very strong influence. So this inelastic, which corresponds to again, is coupling. So coupling to the first excited state is a huge influence. So this rising in the back angle is clearly from the inelastic. But also there's a room for improvement. So first I tried some transfer reactions, like neutron or proton transfer reaction, or 2 neutron transfer reaction, and I could clearly see it's not doing anything. So the influence of transfer is very small. So the next step is to consider the breakup. However, the breakup is five body, because now we have 1, 2, 3, 4 for the projectile and 1 for the target, so it's a 5 body, and this is not possible to perform this kind of calculation. So first we perform the 3 body considering this channel first. Proton plus boron 9 and alpha plus beryllium 6. This is a 3 body, and this we can perform, this 3 body calculation. And actually, by performing this 3 body, I could get some better description of this elastic scattering. But since the error bar is too big, I cannot say anything. I cannot state a too strong conclusion based on this large error bar data. But we can see the cluster configuration might have some influence in this experiment. So actually, what we could perform is that the coupling to the continuum is not important, but description for the carbon-10 as a cluster is very important. So I decided to perform another experiment. So this again, the table where the carbon-10 has a strong deformation as a main effect. But I performed another experiment in carbon-10 on lead at Texas A&M. So they have their Mars, which is their system to produce radioactive ion beam. So we could get some 10 to the 4 particle per second carbon-10. So here is the particle identification spectrum. So we have some small boron-10 contamination, and here's the carbon-10. So we have here the data. So the data very clearly show a strong suppression of Fresnel peak. So here's where we expected the Fresnel peak and have a strong influence. And now we are trying to describe this data. So first we consider just the coupling to the first excited state of carbon-10, and we have a huge effect, but nothing describe the data. So we decided to consider the cluster folding model, the 3 body, like proton plus boron and alpha plus beryllium, but also the data improved, but we could not describe this cross section back here. Here is in the log scale, but here is in the linear scale. So here's the linear scale, this is the log scale, but it's the same data. And we try now, recently, a 4 body calculation. So 4 body calculation, we consider carbon-10 like a boron 8 plus proton. And the description for this region is better. For this region is better described by the 3 body. So it means you might have a combination of this 4 body or 3 body configuration, or the 5 body model would be better to describe this data. However, to perform this kind of 4 body, the alphas and protons and all these possible combination is not possible yet. So we are pushing the calculation by performing this 4 body. For 5 body is not possible yet. So well, that is what I would like to talk. So I would like to emphasize that the low beam can be used to investigate the surface and cluster effect in the elastic scattering. So elastic scattering is a easy process to measure, but it can give some nice, interesting results. And when you do the analysis considering coupled channel calculation, we could show that the different cluster configuration emphasize different channels are affected this elastic scattering. And in particular, the strong absorption or dumping of Fresnel peak from proton rich is interesting things to investigate. And we are now planning to have plans to measure elastic scattering from the nitrogen-12 at energy close to the barrier in Texas A&M and above the barrier at in Lanzhou in China. A list of collaborations. So I have a collaboration from the different labs, like in São Paulo from these Rubinstein groups, in Argentina and at Notre Dame with James Colata, in Texas with Grigory Rogachev. So
Thank you, Professor Baldir, for such an excellent talk, and the presentation was very clear. I think the audience must have enjoyed it. So now the session is open for discussion. So anybody has question can unmute himself and ask the question.
can unmute herself also, no?
Yes, yes, both. Sorry, himself and herself.
Yeah. So I have the question. Can I ask?
Yes.
Yes.
I'm Aradhana Srivastava from BRC. I have a
Okay.
question regarding your data on 6 helium lead and 6 helium on nickel. So my question is that you could explain the data better with four body, considering the four body. So does it
Okay.
mean that two neutrons they are not as correlated, or they are not they need not be considered as dineutrons? Because whereas neutron transfer data shows that these two neutrons are highly correlated. So what is your comment on that?
Well, for the last sketches, it seems that the data has all this indication that the important channel is the breakup. So the breakup was necessary to describe the data. I know for the fusion, I will present again. So just a moment.
Yes. Any other?
Yeah,
Aradhana?
for this elastic scattering, this data was a combination of the data, so there are two data, and it's very clear that for the elastic, this statistic between three body and four body is very important, or more important than transfer. But transfer reaction, is important to describe the fusion reaction. So the total reaction, fusion reaction, the transfer channel is important. But for the elastic, what's important is the breakup channel. Is question.
So I wanted to know if you are treating as a four body, that means these two neutrons are not very much correlated. Because if they are treated as three body, you will consider these two neutrons as dineutrons.
Yeah, so that's the idea. If you do the correlation of these two neutrons, so we treat these two neutrons as a d-neutron cluster, so there is no correlation between them, and if there's some correlation between them, and here you treat them as independent. So in the model, that's right, in the three body and four body model, the difference is exactly how do you treat this neutron, as a cluster or as independent neutrons. So that's question. So for here, you have all the potentials, which is important. So we have here, you have a d potential, which is important. For this, you need the neutron target potential, and also the potential, the bind energy between them, but you treat them as an independent.
Okay, thank you.
So, I mean, if you wanted to go more into details of this correlation between these two neutrons, you have to do some breakup measurement. But for the elastic, what is important is just the model itself, the way you treat as a d neutron or as independent neutron. And then the difference here is the way you consider the potential, the d neutron potential or the neutron target potential, target potential.
Okay, thank you.
Okay.
This is Vinod Kumar. Can I ask a question?
Yes.
Uh, my question is, when you consider a alpha cluster nuclei and there you said reorientation and neutron halo nuclei, there may be in a priori, can you say that it will be a reorientation effect, or it may be a mixture of everything?
Yeah, it depends here. It depends strongly the way you are treating the projectile. Like for Bornel, you treat, you don't treat as a cluster, so you treat as a deformed nucleus. So in this case, you have to consider the quadrupole, so you deformed the potential. And then you need this reorientation, which means it's just coupling to all possible projection of this spin. So when you consider clustering model, like for the bottom 12, which is described as a boron 11 plus neutron, and then it's a different treatment. So the cluster folding model, where you consider the cluster is important. So all this deformation and all this is somehow implicitly taken into account when you describe the projectile as cluster.
Okay, thank you.
So when you, so the idea is to consider, you know, the way you treat the nucleus, or you treat as a deformed nucleus, or you treat as a cluster folding model. It's like for this case, you know, if you treat as a cluster model, you have to take into account all this cluster. So the potential you use in your description is the potential from alpha plus the target, alpha plus the target, and plot of the target. And by this cluster model, you already are taking into account any possible deformation and so on. So you don't need the reorientation. But when you treat as deform the nucleus, then you have to take into account the reorientation.
Okay.
Okay, thank you.
Thank
From
you.
PRC.
Yes.
Can I ask a question?
Yes. Yes. Yes.
Yes.
Yeah. So in this particular case, like 10 carbon plus 58 nickel. So you showed that at larger angles there is a big deviation. It is like looking like a step. Is there any possibility of target contamination, high Z contamination in the target?
What are you talking about this?
Yeah.
Well, the carbon, we have as a backing of carbon, but the backing is so small, I would not guess it was a target contamination, because the target is lead on the backing of carbon, but the carbon was, we have some carbon background, but that was subtracted. So I can check once more about it, but I doubt it's the carbon contamination. I mean, I'm not ruling out completely, but in principle, I would say no, because we have a very small carbon backing. You know? The amount of carbon was very small.
Okay. I have a question. You told about
Okay.
coupled channel calculations, where you said that if you are able to include all the inelastic and transfer reactions, you no need to couple this, include
Yes.
this imaginary potentials, which you have not
Exactly.
done. Which you have not done. But in order to simulate the fusion one, the flux which is going to short range,
Yes.
have you not used for short range imaginary for fusion? That you must have to do, right?
Sorry, say it again.
For you must use short range imaginary potential to simulate the fusion
Yes.
cross sections when you are doing
Yes.
these couple channel calculations. So have you used the short range imaginary potential or not?
Well, yes, I have used the short range imaginary potentials. For all this calculation, we have to use this because fusion is not explicitly taking into account this
So,
coupling channel.
so you have used
So we
it.
have to use the short range, yes.
Okay, okay. No, at one point
And
you
the-
said that you don't need to do that, so I thought maybe. Okay, fine. Any other
Now,
question?
for all this calculation, I still have to include the short range because of this to get into account the absorption channel, so the fusion channel. So I will show you here. There's a discussion of what would be the best parameters for this short range. So this particular paper here, they do some consideration about this potential, and it shows that these parameters are quite reliable to describe the fusion. So that's why we used this short range potential.
Okay.
Because in this coupled channel, you
Oh.
have to take absorption into account. So
Okay.
you have to actually consider this.
Okay, fine.
Can I ask a question? I'm graduate from university. Am I right in understanding that you are considering reorientation or cluster model separately?
I could not hear well, so can you say it again, please?
Am I right in understanding that
Huh?
in the calculation you are considering reorientation separately and a cluster model separately? Can they both be combined together?
Model. No. Because
But
you see, that's what I'm saying. You have two ways to treat. One way is by considering the nucleus as deforming the nucleus. And in this case, the quadrupole moment is important. And then you have to make a projection of this spin on the axis of collision. And for the cluster model, cluster folding model, you don't have to do it. So there are different ways to do it. So you cannot mix, because in this cluster folding model, you don't include any deformation. What you do is just to account the clusters. Of course, for beryllium 11, it's well known that the core has excitation. And then in this case, you can take the deformation of the core. So it's very fancy calculation and performed by very few people. And what they are doing is they are considering the deformation of the core. So not the beryllium 11, but deformation of beryllium 10 plus the neutron. So that's not what I'm doing. What I'm doing is, or I take in the nucleus as a deformed nucleus like boron 10 and boron 11, or I consider like a cluster folding model. In this case, the deformation is implicitly taken by the folding model, and I don't need this reorientation effect.
in reality, could they both be coupled? Like reorientation might bring in a cluster at different angles, and its a breakoff might be different. So they might be both coupled.
Okay, well, I don't know.
Okay, thank you, Professor Baldir. I think we should stop and go to next speaker, and because
Okay,
time
thank
is
you very much, and
yeah.
it's a pleasure for me to give this talk. So thank you very much.
You're welcome. So now we'll go over to next talk. I request Abhijit to show the next one. So next talk is by Akhil Jhingan from Inter University Accelerator Center, New Delhi, India. So let me tell brief something about him. So after completing his MSc Physics in 1996, he joined IUAC, Inter University Accelerator Center, in 1997. Presently, he is a scientist at the level of F, and he is heading the Detector Development Lab, IUAC, and he is a co-principal investigator of NAND project at IUAC, funded by DST. And he has done his PhD from Punjab University, Chandigarh, under the supervision of Dr. Vibhas Behera. His research area includes development of charged particle nuclear detector instrumentation, position sensitive gas proportional counters, ionization chambers for particle identification, cesium iodide photodiode detector instrumentation for particle identification by PSD, development of hybrid preamplifiers, which is charge sensitive and fast timing for signal processing. Beyond the academic session, this academic session hours of symposium, conferences, meetings, etc. He is one of the must-have friends of Dr. B.K. Nayak. We are happy that he is actively participating in this webinar and agreed to give a talk on charged particle detectors for fusion fission measurements. So I will now request Akhil to present his talk. Akhil.
Yeah. Thank you, Dr. Santra. I hope everybody can hear me.
Yes, I can.
Yes.
Yeah. So I thanks the organizers for giving me the opportunity, and let me open my presentation. Slides are visible now?
It's coming. Yes, visible.
It's coming. Yes.
Yeah. So I will be talking about the charge particle detector instrumentation for fission measurements, and let me thank the organizers for giving me the opportunity to present my work, and especially when it is coinciding with the 60th birthday of our friend Professor Basant Nayak. And also he is a superannuating after a very illustrious career and active career, and I wish him good health and active life in the future. And it's known that this fact that the academicians never retire, and even after retire they continue to contribute in the area of research, and hope Dr. Nayak will be also active and provide his guidance in all things. So I've known him from say last almost now 15 years. Of course, when I joined 97, he was a well-established person, but my association with him starts from 2004 when he and Dr. Saxena visited Delhi in one of the scattering chamber experiments, and we became very good friends. And it is of course a known fact that like-minded people become friends very fast. And though he was very senior to me, but still, of course, he treated me like a friend. And as Dr. Santra said, that we have been very good friends, symposium or post-symposium or whatever it is. And I will be presenting my work, which will involve association with Dr. Nayak. And these involve experiments like mass distributions, fission mass distribution and angular distributions, and then neutron and light charge particle multiplicity measurements gated by fission, and then in recent time quasi-elastic scattering measurements. And this is a big collaboration generally involving IUAC, Punjab University. Punjab University, Chandigarh in particular, has been very active in this collaboration. And we have a long history of collaboration with involving this Punjab University, IUAC, BRC, and not only Dr. Nayak, Dr. Saxena, Dr. Kailash, Dr. Chaudhary, and it has been then Dr. Santra, Dr. Ranju Thomas, in recent times Kripa, Radhana Srivastava. So we have this big collaboration, and that involves your Central University, Kerala, Delhi University, and Banaras Hindu University as well. And the facilities that we have used is our general purpose scattering chamber, and in the last few years this national array of neutron detectors has come up, which is a facility that has 100 cylindrical DC501 scintillators arranged in a geodesic dome, with the detectors placed at 1.75 meter from the target. Solid angle coverage is 3% of 4 pi. And then at the center we have a scattering chamber of a diameter, spherical scattering chamber of 1 meter. I think you can see this spherical scattering chamber here, which houses the multi-wire proportional counters for the fission experiments. And in recent times we have used this chamber for performing quasi-elastic scattering measurements and fission angular distribution experiment as well. So these are the typical liquid scintillators, and this is the setup for data acquisition. And detector development activities that involve charge particle I will be talking about. These are multi-wire proportional counters position system, and then gas ionization chambers for particle identification. Then we have used this silicon strip detector systems also, gas silicon hybrid system. And in the recent times we have been doing fission gated and fusion gated light charge particle measurements. So we have this cesium iodide coupled to photodiode detectors, and these were required ready-made from Xionyx, but it's a complete instrumentation that involves your hybrid preamplifiers, and pulse shape discrimination systems have been developed in-house Of course, these again we use some commercial equipments, spectroscopy amplifiers and all, and development of charge-sensitive preamplifiers and fast-timing preamplifiers that can operate inside vacuum. This in-vacuum operation of preamplifiers has been a game changer for these kind of measurements. And in our earlier days when I joined and we were performing experiments, most of these preamplifiers were placed outside the chamber, and our half of the time in the experiment used to go in reducing the noise, wrapping this aluminum foil, braided wires, and that was a terrible time. But after we operated these preamplifiers inside vacuum, these homemade preamplifiers, we could get rid of noise, I can say, and the measurements became much smooth. So I will talk about first is a hybrid telescope array, which we have developed for quasi-elastic scattering and fission angular distribution. And this quasi-elastic scattering measurements were proposed by Punjab University group, Professor Bera and his students Gurpreet Kaur. And these measurements were supposed to be performed with LINAC, and the system was 48 titanium on 238 to thorium. And normally whenever we perform such measurements, barrier distribution, we record the data in 1 or 1.5 MeV steps. But whenever you are performing an experiment with the LINAC, your currents are very low. And especially when 48 titanium, you are accelerating, say, at 300 MeV. So it is simply not possible to perform these measurements at 1 MeV steps because of the low flux. So we were wondering whether we should reduce this energy steps. And it happened when these experiments were proposed, Dr. Nayak happened to be at Delhi, and he passed on us a thesis. This was a iThimba lab thesis where they have performed this quasi-elastic scattering, and but they have taken larger energy steps, but at the same time they have taken data, backscatter data at larger angles, and then they correlate later on with the measurement of different effective energies. Yogesh Gupta has already described this technique yesterday very beautifully, so I will not go into the physics part. And on his recommendation, then we decided to develop this array. And to start with, we had only 3 telescopes, which were initially developed for fission angular distribution measurements. This was again a Punjab University measurement way back in 2011. And later on, we decided to develop a dome with 4 telescopes for this quasi-elastic scattering measurement. But then as things developed, we added more telescopes so that we can measure more effective energies at different angles, as I had discussed. So this was the first measurement that was performed in, say, somewhere in, I think, 2014, and the system was 28 silicon on 154 samarium. And this was again the thesis work of Punjab University student Dr. Gurpreet Kaur. She is now a postdoc at Sao Paulo, and this was her second measurement. This is a 48 titanium or 232 thorium. You can see large number of telescopes we mounted, and in the first measurement we had these telescopes at 170 degree, and for the second experiment we mounted these telescopes at 173 degree, and this was perfectly aligned, the system. And this data has been analyzed and will be shortly communicated. And this is how these hybrid telescopes look like. And this has a silicon detector as a E detector and a gas ionization chamber in axial field mode. We have a anode sandwiched between 2 wireframe cathodes at, say, about 1 centimeter separation. And these are the measurements that have been performed. This was the first measurement in 2011. with only 3 telescope fission angular distribution. This has been recently communicated to EPGA, and you can see the fission channels very well separated from your projectile-like fragments. And later on, we performed the quasi-elastic scatter measurements, 28 silicon on 154. It has already been published, and these are the barrier distribution. I think Dr. Behra will be talking more about this barrier distribution part tomorrow in his talk. So I will only keep myself focused on the detector part, so one can see how these various reaction channels can be cleanly separated when you do this delta EE measurement. And gas detector has an advantage because I think probably yesterday Professor Dr. Yogesh Gupta presented, if you have a silicon delta E detector, chances are very high at very low energy your projectile-like particles are going to stop within your delta E, and it becomes very difficult to separate different channels. But gas detector, you have the flexibility, you can vary the thickness by varying the pressure. And this was and later on we performed many measurements, and with this quasi-elastic measurements. Oxygen on thulium is one setup which was performed, and this measurements were performed by Dr. Abhishek Yadav at IUC. And again, you can see at different energies, this is a 173 degree data, how we are going from pure elastic to quasi-elastic and breakup events, so on. And many such measurements have been performed recently with the experiment performed by, again, Punjab University group, silicon on 144 samarium, continuation from silicon to 154, and then IIT Ropar has performed measurements, and with lithium beam, lithium on tin, and Vishwa Bharati University has also performed one measurement, silicon on neodymium. And coming to the front-end electronics, as I told you, this is when you are using large number of telescopes. We have 16 telescopes in this array, so you need a high-density instrumentation also. And to keep noise at bay, we developed this hybrid preamplifiers with 2 gains, 20 millivolt or 10 millivolt per MeV for silicon. Of course, when we went for this LINAC measurements, we went down to 3 millivolt per MeV so that they don't saturate. At low power, the dynamic range is low, 30 milliwatt we have to keep, and 90 millivolt per MeV for the gas part, because gas energy loss is very less. And these are the hybrid preamplifiers which were developed. You get this small with very low power consumption of 30 milliwatt at plus minus 6 volt. And at such low power also you can see the performance. This is the spectra taken from the mixed source, and you can see even all the channels of this alphas are well resolved. This is 5.48, 5.44, 5.39 MeV, and this is the beauty of this hybrid preamplifiers. It gives you a very clean signal, noise-free signal when you are placing them inside the vacuum. I can show you the picture. These you can see these preamplifiers. So this reduces the cable length when you are putting them inside the chamber. And these are then interfaced with your Mesitech preamplifiers. So 32 channels and this much of electronics only, and this is your power supply units. And these the detectors are mounted in 3 groups, one forward angle, one backward angle, and then also at the 173 degree. So we can independently vary the gas pressures, and we had 3 gas handling systems operating at that time. And you can this also helps us to check the leak. In case there is a group leaking, we can control the gas pressure, otherwise it affects all the detectors. So, and other part is your this fission gated light charge particle multiplicity measurements, and was very actively involved. And to start with, this was a thesis measurement of another Punjab University student, Dr. Kushal Kapoor, and Dr. Ashok Kumar, Dr. Behra, Dr. B.K. Nayak, Dr. Saxena. All of them were collaborators in this measurement. And similar measurements had already been performed at BRC by Yogesh Gupta and so on. And we also went ahead with these measurements. So we developed again a 16 detector cesium iodide array. So we had this 2 centimeter by 2 centimeter cesium iodide detectors mounted in groups of 4 to have a large solid angle coverage, and these detectors were placed very close to the target. And again, we developed this custom-made instrumentation in-house. These are your charge sensitive preamplifiers placed at the back. So this completely eliminates the cable between your cesium iodide and preamplifiers, because cesium iodide gives very low signal, which tends to merge in noise. Integrated preamplifiers. And for pulse shape discrimination, we used ballistic deficit technique, short shipping time and long shipping time technique. And for that, we used Mesitech spectroscopy amplifiers with 0.5 microsecond and 3 microsecond shipping time. And to interface these preamplifiers with Mesitech, which have a differential input, we developed a single end to differential active converter unit. So you have a single-ended input and you get a differential output. This is a op-amp based circuit, and this is the layout. So you have this 12 detectors you can see, and this quad is placed right at the back of the fission detector, a transmission type. So you have a oxygen charge, this multiplicity being measured at the same time. Later on, we replaced this daughter card by a new thing, and this is actually really a benchmark development, I will say. So you have 4 preamplifiers you can see, and this really makes the things much more compact. And these were fabricated using chip resistors and capacitors, which have a size as small as 1 millimeter by 0.5 millimeter. And you can see the performance when you have this integrated system. Very clean separation of this thorium-229. Resolution was close to 3%. These are the gamma spectrum, and this is the time of flight, timing with this cesium iodide detectors. And this peak width is, I think, close to 12 to 15 nanosecond, which is very good if you talk about with a slow detector of like cesium iodide. And this is the particle PID plot generated from this ballistic deficit spectrum, long shipping time against PID. This is short shipping time ratio of short and long. And these are the measurements performed of our oxygen on platinum from fission gated this alpha spectra. So now I move to this multi-wire proportional counters detectors from this hybrid to that. And these detectors we have been developing from I think late 1990s, and we started with multi-step counters with 4 or 5 electrode geometry inspired by the design of Breskin in late 70s or early 80s. And gradually from multi-step 2 we came to the conventional 3 electrode one. And again here also we made a lot of modifications. We started with 1 millimeter pitch, and nowadays we are developing detectors with 300 micrometer wire pitch. Shorter the wire spacing, higher is the gain, faster is the charge collection, better is the timing we get. And we developed start-stop detector systems, and position extraction is through this delay line technique. And these are the various geometries. This is the conventional 3 electrode where you have a mylar foil which is aluminized on both the sides in the center, This is sandwiched between two wireframes or anode, which are position sensitive, and these are connected by a delay line. And this is the multi-step counter, where you have a pre-amplification region at the entrance and then the avalanche region in the center. So many detectors have been developed. This is the first one for the fission measurements that we developed. 8-inch by 4-inch active area. This was a 5 electrode geometry, and you can see the performance, position resolution, close to 1 millimeter have been achieved by this. And then we had a start detector to have a start-stop detector system. So, and this is the performance. You can see if time of flight with respect to the RF from the accelerator, your reaction channels, projectile-like, fission fragment, target recoils are very cleanly separated. This is for the system fluorine on 206-208 lead. This was a thesis work of our student Rakesh Dubey. And many such measurements have been performed, and this is again a BRC work by R.G. Thomas and a student C. Yadav. And by applying various calculations, you can make a spectra very clean. You can separate the transfer-induced events from the actual fusion-fission events and or quasi-fission events and so on. And this is the start-stop detector system. And this start detector was initially, of course, developed for our offline activities when we used to, say, calibrate our fission detectors or characterize them. So there is no time of flight or RF given. So this was developed so that you can have a Californium source with, say, fission and neutron, and start-stop. This system will give you the time of flight and so on. But its actual online measurement first time was used in, say, early 2010. And this was again a BRC group experiment. And measurements were performed with lithium on uranium. And somehow our accelerator group could not provide us the pulsed lithium beam. So I consulted Dr. Nayak, Dr. Santra. They were leading this measurement. And I offered them, if we have this start-stop detector, are you willing to take the risk? Because you have these two Mylar foils coming in the picture, which will have some straggling. And they agreed, yes, we should go for this kind of measurement. And this was used in their experiments. And I will come to the results later. And later on, we went to for 3 electrode geometry for NAND. And this is another detector with active area 6.4 by 4.4 inch. And from 1 millimeter wire pitch, we went to 0.63 millimeter wire pitch. And we reduced the wire diameter to 10 micrometer to have higher gains. And you can see in our earlier detectors, we were using this Rhombus commercial delay line chips. And when we reduced the wire pitch, these chips were not useful anymore. So we developed in-house a delay line. You can see with the chip inductors and capacitors to maintain the position resolution. So this is again a start-stop detector system in GPSC. This is again Dr. Santra's experiment, lithium on uranium. First experiment was performed in, say, 2010, and again we performed another measurement in 2014 with cesiumide detectors for this charge particle gating, 16 of them. This is the rise time with the start detector. You can see rise times say close better than 2 nanosecond. A microchannel plate gives you typically a rise time of, say, 1.5 nanosecond. But with a multi-wire counter also, we have achieved, say, better than 2 nanosecond rise times. And this is the quality of signals, all better than 1 volt pulses for your fission fragments. And these are the position spectras. And this is the online spectra for lithium on uranium. You can find these results in these two publications. And you can see this 6 lithium breakup into deuteron or alpha and so on, these reaction channels are very cleanly separated. And this is the raw charge particle spectra from cesium iodide. And once you get them with your fission fragments, you can see all these are very clean channels you can have: alpha, tritium, deuteron, proton. And when you get them with the fission fragments, you can identify, you can see all kind of channels, tritium, alpha gated. This is available, results are available in this rapid communication by this group, Asim Pal, Dr. Santara, Dr. Nayak, and so on. And these are our measurements in the neutron chamber. And this is a Punjab University measurement, mass-gated neutron multiplicity. This was a thesis work of Dr. Meenu Thakur, and this came out in 2018. So this is 48 titanium on 208 lead. And similar measurements have been performed with 50 titanium beam on 208 lead in Lignaro by the Aparna Babu et al. This was again BRC LNL collaboration. And they performed it with microchannel plate, we performed it with MWPC, but I believe the results are not very different. You have a very clean spectra. There are sometimes a mechanical constraint, some measurements where we are forced to bring the detectors much closer. Generally, we prefer a 30 centimeter flight path for good separation. But with experiments such as 48 titanium, when we accelerate it through LINAC, your currents are very low, as low as say 0.2 to 0.3 PNA, and we require larger solid angle. So we bring these detectors much closer, and there's a possibility that you may have shadow of target ladder. So what we did is we interchanged this X and Y. You can see now it has a bigger acceptance in vertical and so on. And this increased our solid angle very much. Angular acceptance was plus minus 20 degree in horizontal and plus minus 70 degree in vertical, 16 centimeter flight path. And these measurements were, say, for system titanium on samarium, titanium on gadolinium, and silicon on hafnium. These kind of measurements have been performed by Punjab University, Calicut University, Central University, Kerala, Delhi University. These were the group which they performed these measurements. And for very asymmetric systems, say silicon on thorium, we are placing the detector one in forward angle, and this we went as close as say at 28 degree from the target with respect to the beam direction, and with plus minus 15 degree angular acceptance for forward angle. So we are measuring, say, typically from 13 degree to 43 degree. So we are gone very close, and the beam flux is very high in such cases. But then we got very good data when you, even with low flux of currents, and at such short flight path also the resolutions were very good, timing resolution, both from the accelerator side. We were using the RF pulse, and you can see we get very clean separation between the various channels. This is the thesis work of Dr. Ruchi Mahajan, a student of Professor Behra, the mass distribution measurements, and you see the latest results. We have a very clean data. This manuscript is under preparation, and this is the work of Dr. Neeraj Kumar from Delhi University, and this manuscript has been just communicated. Silicon on hafnium and titanium on gadolinium. You can see we have again very clean data and very clean separation from the various reaction channels. And now coming to this measurements at TFR, and some point of time we had a plan to develop a new scattering chamber for our Beam Hall 2 facility. And Dr. Sugathan, he advised me that I should make a visit to TFR and look at their chamber, new scattering chamber, whether we can duplicate the same and have in BMOL 2. And then I approached Dr. Nayak, and if you can allow me to visit this scattering chamber facility. And he was very generous and polite. He said, why not? You are very much welcome. This scattering chamber also belongs to you. And you can probably come and participate in a measurement also. And then at that time, Rahul Tripathi was planning these measurements, chlorine on samarium. And when we discussed these measurements, so initially I think this experiment was supposed to be performed with a silicon strip detector, but I offered, if you can use a multi-wire proportional counter, you will have much better data. And initially, I think due to noise issues, they were reluctant. The scattering chamber has a lot of noise, so maybe gas detector, whether it will be useful or not. So I, that time, came up with this idea of placing this fast timing preamplifiers. Earlier, we had never used them in the vacuum at IUAC. These are homemade and developed. But we can get rid of this thing if we can operate this in the vacuum. So Dr. Nayak said you will get the full support, and this is how I joined my first measurement in TFR. I think this was in 2014. Chlorine on samarium leading to 179 and 191 gold. And this was a very hot topic. Now also it's still a hot topic, asymmetric fission in mercury region, 180 mercury region. And this was, I think, the first measurement of its type, this asymmetric fission in 180, this mass region in the country, if I am correct. And this came out later on in Physical Review C. And more about this detectors you can find in this publication in Pramana. This was the proceedings of the Fission 75 conference. So you can see we have a very clean spectra in this case. These are the fusion events, and these are your elastic events. And these are the asymmetric fission results. And this is what I was talking. Initially, we had this kind of 8-channel NIM module, which we placed outside the vacuum to get the timing signals from the multi-wire proportional counters. And then for in vacuum operation, we developed this kind of thing. First, we operated in TFR, and then now we are using them routinely inside vacuum in our NAND as well as GPSC scattering chamber. And this collaboration continued thereafter. And I think Dr. Kripa Mata has a talk on this asymmetric fission part in this mercury region tomorrow or day after tomorrow. And these measurements were later extended, chlorine on samarium with the 16 oxygen on lutetium. And one similar experiment was performed in collaboration with Ganel Group at IUAC also. And these results just, I think, came out this year in PLB, the thesis work of Shilpi. And again, I visited TFR. We had another measurement. These are surrogate reactions, lithium on uranium and thorium. And I was again part of this measurement. These proportional counters at back angle for fission angular distribution in coincidence with the breakup of this projectile-like events in silicon strip detector telescopes. And these are the results. These are the gated spectra from fission with your silicon strip detector events. So, boosted by this, we developed a new detector system at IUAC, ER-gated neutron and light charge particle multiplicity measurements in scattering chamber. This is again thesis work of Hani Arora, student of Dr. Mehra. So we developed 2 new counters, and you can see these counters were placed very close to 0 degree in the scattering chamber, and the proportional counters were custom made for these experiments. We had a cutting at the edge so that the beam can go through and we can go as close. So beam is going in this direction. and we have an angular coverage, say from 2 degree to 10 degree for the ERs, and at such high angle, it is exposed to all kind of junk, target recoils, elastics, and so on. And this was the time of flight spectra from the ER. We got ER time of flight against the residual energy. But when we get it with your neutron and charge particle events, so this is the fusion ERs, spectra becomes fairly clean. And these are the charge particles cesium iodide for your alpha gated spectra. Neutron detectors are outside the chamber, so this is still under analysis. So we really could not perform the experiment the way we wanted, because the flux was so high that we were forced to operate the proportional counters at lower potentials because it was breaking down, and this spoiled our position spectrum. We could get at lower potential the time of flight spectra, but these position signals were very poor. So we are now making modifications in the design so that the next measurements that we perform, maybe in the NAND scattering chamber, we will have good signals on that also. But everything comes at a cost when you operate the detectors at the limits. So aging effects are also faster. So we found that our proportional counters that we were using in the NAND scattering chamber for fission mass distribution, the gains have reduced, the signal strength had become very low. And so when we opened the detector, we found this kind of compound formation on the detector, this cathode foil. And you can see these structures which similar to our wire structure. This compound formation has taken place. So this is after 3 years of use. So periodically we have to replace the foil as well as the wire frames. Okay, if this has got damaged, so wire also aging also must have taken place. So we have to replace them now periodically when you operate them at limits. So I will come to my last this work, this integrated MWPC silicon detector. This was in collaboration with Ganil, and they had an experiment at IUC as well as at Ganil, and Dr. Naveen and Dr. Crystal Smith, they approached me whether I can develop a detector which doesn't have a foil between a large area silicon strip detector and a multi-wire proportional counter to be operated in the target chamber of the VAMOS scattering chamber. And I took up that challenge, and they provided me with the silicon strip detector. And again, the challenge was no foil between your silicon strip detector and MWPC, because we were planning to measure both velocity and energy of the fission fragments, which is called a 2V2E kind of measurement. And I replaced the central cathode foil with a Mylar, this wire frame. But to preserve the timing, we reduced the wire pitch from, say, earlier we were using 1 mm, we went to 0.6 mm, but then I went to 0.3 mm, and this really worked. So this was a 3 electrode geometry where the anode position frames had a wire pitch of 0.6 mm, and this timing cathode at 0.3 mm. And this is the typical layout. And this really worked very beautifully. And I again tried new fancy things. I integrated the charge sensitive preamplifiers with the detector body as well as the fast timing amplifier. And this is how the detector looks like. These are the delay lines, inductors and capacitor. This is the 5-channel preamplifier card. And this really gave very clean signals in the Ganil measurement. This was a 10-day measurement with the delay line readout. And they had experienced problem with their kind of design, which uses 1 mm wire pitch, 3 wire frame. And they were forced to discard your delay line method. And they are using your this Gacyplex chips, which have charge sensitive preamplifiers. But this really worked, and this work was very much appreciated. This was again to observe the asymmetric fission in Mercury region. This was an inverse kinematics measurement. And these are the quality of signals we get. For a 5 centimeter flight path, time of flight against energy, you can see what a clean timing and energy versus time of flight path. So this is the layout, and these are the results. You can see the quality of spectra between energy and this timing, how this position signals are cleanly separated when we get the position spectra with one strip of the strip detector. This one strip is something like 4.5 millimeter wide, and these are the energy correlation gated from the focal plane spectra, and these are the time correlations, these are the fusion-fission events, and these are the elastic events. So this manuscript is under preparation of these results. So I come to the end of my talk. I thank all my collaborators and my colleagues at IUAC who have helped in this development of this detector activities, and thanks.
Thank you, Akhil, for another excellent talk. And you are the detector man, who showed the evolution of different detectors. And it is nice to know that you have been able to develop the detector which can measure both time of flight as well as energy, which we are looking for. Actually, we planned several experiments to do using this kind of detector, which I already discussed with you. So it's really thankful to you, and it's a nice presentation. So thank you again. So now the session is open for discussion. So one can unmute oneself and ask the question. And Sanat, if there is any question from YouTube, that also you can tell. You can forward it.
This is R.K. Chaudhary.
Good evening, sir.
Hello.
Hello, good evening, sir.
Yeah.
Yes, sir. Yes, sir.
This is such a beautiful presentation. I couldn't stop, wondering how a committed developing equipment developer can really make a lot of difference in the experimental programs, without which I think it's all impossible to carry out these measurements. So I must really congratulate you. And you have tuned your developments. That is also very important to the need of the experimenter. This is very rare combination, and I think you have to also see that this trend continues in IUS by training more people to do this kind of joint activities to really strengthen our efforts. I think the other thing that I also feel is that such detectors will be useful when we develop rare beams, and that is where I think India has lacked for a long time. Although in other countries they have done a lot of work in this radioactive and exotic beams, we have not been able to do. But your detectors, which are very large Fred angles and very good discriminatory capacity and all that, can really help in that process. So at this time, I would like to urge the Seoul nuclear community to really go for full-fledged way, go out of your shell and try to develop new accelerator systems, new facilities, so that these detectors will be also sort of very useful in trying situations. So let me anyway wish you all the best, and thank you for this nice talk.
Thank you very much, sir, for your appreciation of our work. Thank you very much.
Dr. Chaudhary, I would like to inform you that in collaboration with Akhil in BRC, we have been able to develop two MWPC detectors, and which has been used by the PhD work of Asim Pal, who is in our group. So that also we have started using for several experiments. We have successfully done the experiments. So yeah, there is some question. There is some question from YouTube. There is some question from YouTube for Akhil,
Yeah.
that what is the improvement when you reduce the pitch from 1
Yes.
millimeter, and what is the improvement in time resolution? So these are the two questions.
Okay. See, the gains increase by a factor of almost 3 to 4 times. So, as far as timing is concerned, see, these are induced signal, and the maximum time taken by the charge to induce the signal on the wire is equal to the half the wire spacing. So when you reduce this wire pitch, obviously the charge collection times become fast, so your timing improves. So you go from 1 mm to half mm, it will improve by a factor of at least 2, and the gains can improve by a factor of much more, because this pre-amplifiers that we use are bandwidth limited. Faster the charge collection, higher is the gain. For example, if the gain is say gain is 100 for the pre-amplifier, this gain will be 100 for the pre-amplifier for a rise time of say 2 to 5 nanosecond. If the rise time is 10 nanosecond, then the gain will be reduced to half. So indirectly, the gain is increasing by a factor of say 3 to 4 times when we reduce the wire pitch by half. And further, when we go to 0.3 mm, so we have seen a huge jump in the gain.
Okay. I think there is another question.
Akhil?
Asim,
Yes, sir.
How are you?
Fine, sir. Fine, sir.
So you are using this star detector only for one side or both the sides?
Sir, we have research.
Study.
Yeah, we have used it for both the sides for this Santra and Asim Pal's experiment that was done in 2016, I think maybe. So there was a paper also. I think you are a co-author in that paper.
No, but then what are the time resolution improvement in that compared to your one side when you use the detector only one side?
I don't have a spectra right now, but we use this start-stop detector measurement in a offline measurement with a mixed this alpha source, plutonium, amnesium, and curium. So in a 30 centimeter flight path, we could separate plutonium, amnesium, and curium. And for alpha, we had a resolution of say close to 450 picosecond. For fission fragments, since pulse heights are much stronger, I expect this time resolution should be around 100 to 150 picosecond.
okay. There was another question from YouTube. Abhijit, can you repeat that? Actually, I missed that. Maybe you can unmute yourself and just tell it. Abhijit, are you there? Yeah, one can see in the chat. Yeah, please ask, what is the energy resolution of the detectors for beams like 6 lithium and 35 chlorine? That was the question.
The resolution of which detector?
Resolution, yeah, I don't know what he intends for. Probably.
So for multi-wire proportional counter, there is no energy.
There is no energy resolution.
Timing
Yeah.
resolution.
Yeah.
Yeah.
So, so there is no question.
Okay, I have one question. When you reduce the pitch and then you have the large number of delay lines, so you get lines. So
Yes,
in
sir.
that case, what kind of signal attenuation you are seeing there? Because when you have large numbers, do you use any kind of an amplification in the midsection or somewhere, or it is a single line which is going through?
Okay, I will answer this question in 2 steps. First, when we reduce the wire pitch, your gain of the detector itself has increased. Now coming to the attenuation part. See, for our earlier designs, we used a delay of 2 nanosecond per tap. But when we reduce the wire pitch, obviously the delays also, lines also have to increase. So we reduce this delay value from 2 nanosecond to 1 nanosecond per pitch. So that reduces the attenuation. Coming to additional amplification, these position signals are almost say 1/5 or 1/6, or maybe smaller than your actual central timing signal. So we generally provide them an additional amplification with this Philips 777 or 776 amplifier unit for the position signals.
Thank you.
Okay, if there are no more questions, then let us thank the speaker again for his nice talk with such a nice background of development. And thank you, Akhil, once again.
Okay, thank you, Dr. Santra. Thank you very much.
Yeah, so we'll now go to next talk, the third talk and the last talk of today's webinar. So may I request Abhijit to show the abstract? Yeah, Akhil, you should stop presenting.
Okay.
So maybe I'll say a few words about the last speaker, who is Professor Indranil Majumdar, and he's a full professor at TIFR, who has graduated from Delhi University and did his PhD from IUSC, jointly from IUSC and Delhi University. He has done his postdoctorate at State University of New York at Stony Brook. Later he extended his sabbatical at Duke University. To his credit, he has been awarded the DST Sarna Jayanti Award. His research interests are very broad, starting from theory, experiment, and as well as instrumentation. In theoretical studies, he has done this on neutron, this rich halo nuclei, Ephimov effect, few body dynamics, several major first-time theoretical prediction, and a book written by him, which will be published by Springer, which is in press. And on experimental work is mainly on GDR decay studies, fusion fission, and light ion scattering. And his current interests are in nuclear astrophysics. And in instrumentation part, he has designed and built several major arrays of scintillation detectors, sodium iodide, lanthanum bromide, etc. at IUSC, Stony Brook, and TIFR. Professor Majumdar is also a very good friend of Dr. Nayak and has spontaneously agreed to talk on nuclear capture and inelastic reactions to study nucleosynthesis. So may I now request Indranil to start his presentation.
Is it coming?
Not yet.
Now?
No, not yet. It hasn't come.
No?
No.
Is it there?
Start presentation. Present now. There is, when you go, no? When you take your cursor down. Yeah.
Okay, sorry, I have to share it. Okay, so it should come now.
Yes, it has started coming. Yeah.
Okay.
Yeah.
Is it okay?
Full presentation. Yes, it has come.
Okay.
Now you can start.
Thank you, Shatranjan. Thank you, Dr. Satra, for a very kind introduction. And I am indeed delighted to get this invitation and this opportunity to talk to friends and colleagues on this very special occasion when we are felicitating our highly respected and my senior colleague, Dr. V.K. Nayak, and also a very long friend. It has been a great pleasure and have learned a lot from him, and his style of working, particularly in science and physics, has been actually very inspiring to me. And these are just not mere words. So I am very happy to be part of this 4 days webinar. So let me start my presentation It is titled Nuclear Capture and Inelastic Scattering Reactions to Study Nucleosynthesis. So this title actually needs some explanation, and this is because like most of a heavy ion physics person, so light ion physics for me is a very fledgling field where we have started very recently. The reason is, if you look at the nuclear physics community in India at large, so in nutshell, one can say that we are primarily heavy ion centric researchers who are working in fusion fission reactions, fusion evaporation reactions, deep inelastic reactions, transfer reactions, elastic and quasi-elastic processes, etc. And you will hear, you've already heard, and you will hear a lot about it in the coming days also from other colleagues. And the universal goal in this for last 40 years or so is basically to understand nuclear structure and structural evolution with temperature, angular momentum, and isospin. And also in parallel, people carry out work on reaction dynamics below, above, and around the barrier, something in which the Indian community is very, very active. Going high up in the energy ladder, people also have been working in plasma, relativistic heavy ion physics, etc., in which we have international collaborations in experimental part and a lot of theoretical activities. So the major existing accelerator facilities, primarily I mean the heavy ion physics facilities, are in Delhi, Bombay, and Calcutta, the Peletron Linac facility at TIFR BRC facility in Bombay, and also the Peletron Linac facility in Delhi, and the cyclotron facility in Calcutta, and the superconductor cyclotron is coming up. However, nuclear physics is a very broad canvas, and its charm lies from radioactivity to RIC. So if we are fully concentrated only on one dimension, maybe we are missing other interesting dimensions. So there are several other dimensions. As far today's talk is concerned, I would just like to harp upon nuclear astrophysics. And now, before I start presenting our very simple-minded some results, I will give some elementary introduction, which is basically known to all of you. And we'll also talk a little bit about instrumentations by which we actually carry out our measurements. So in nuclear astrophysics, as you all know, the goal is basically to understand the life cycle of the stars, the energy production mechanism in the stars, the formation of the elements, nucleosynthesis, either within the star or outside at different sites. And in these, we cannot forget that the overarching role of nuclear physics. Somehow over the years, there has been some disconnect between the astrophysicists and the nuclear physicists, but nuclear astrophysics is something in which the nuclear physics is almost supreme. Whether it is the understanding of the structures, decay of them through alpha decay, beta decay, gamma decay, fission, or the importance of the understanding of nuclear level density, nuclear levels, their resonances, their strength functions, etc. And also the different types of reactions, primarily capture reactions, and inelastic scattering also, which are very important to understand various mechanisms which are going on at different astrophysical sites. So in this process, the role of nuclear-nuclear interaction is also very important. And not only that, even neutrino-nucleon interactions. I mean, it is a fact that if we are really talking about supernovae, etc., or the jets and the nucleosynthesis process there, it actually get affected by the neutrino-nucleon interactions. So, as you all know, this is very well-known plots. On the left side is a very simple-minded Big Bang nucleosynthesis. So nucleosynthesis we can actually understand in terms of different epochs and different sites. So primarily if we talk about Big Bang nucleosynthesis, that everything will happening within the first 1 to 2 minutes or so, and that there are very few proton, deuteron, helium-3, lithium-6, lithium-7, etc., and that's it. However, as of today, if we look at the abundance chart, then that is what we see on the right side. And then, so basically the challenge to the physicists, nuclear physicists, astrophysicists, is to explain this. What is the abundance of any isotope present and why is it so? So basically this subject is a confluence of nuclear physics, atomic physics, and of course particle physics, plasma physics, cosmology, and gravitation. So as I said, we cannot really do things randomly. There are basically 3 different epochs. One is the Big Bang nucleosynthesis, mostly when we are producing hydrogen, helium, lithium, deuteron, etc. And then we also have slow, or the so-called quiescent process, which takes over a long period, sometimes billions of years, like what is happening in the sun or sun-like stars or even heavier stars, which is the stellar nucleosynthesis. So the temperature is actually very moderate inside, around 10 to the power 6 or so, like that. And also we can have fast, explosive, cataclysmic processes happening in which we produce elements which are above the iron or so. So since we are basically will be addressing something like related with Big Bang nucleosynthesis in this talk. So let's look at the left side in the down there. So as you see, with time and temperature, time is up there, and the different masses. After around 1 minute or 2 or 3 minutes or so, more or less, you have all the elements which are present there, and then they will remain like that, remain constant till the star formation takes place. So that is one region of nucleosynthesis. One is interested because this is very interesting because it is directly related with cosmology and the other astrophysics thing. And on the right side, we have our very favorite well-known Gamow plot, something which we have to be very concerned about when we are talking of stellar nucleosynthesis having inside the star. So now I talk of formation of heavy elements. I mean, the formation of heavy elements beyond the iron, the Coulomb barrier is too high. So the nucleosynthesis is basically happening through neutron or proton capture processes. The neutron capture processes are basically two types. The slow process, where the environment is such that the neutron numbers are not very high, maybe let us say around 3 into 10 to the power 8 neutrons per centimeter cube. And this is the slow process. And so there is a competition going on between the neutron capture and the subsequent beta decay. These are processes which are generally happening along the line of beta stability in the Segre chart. And the most important thing, two very important reactions one should always remember, are this 13 carbon alpha going to neutron and 16 oxygen, and then 22 neon and alpha and neutron going to 25 magnesium reactions. And these are the reactions which are actually produced, if you want to ask that what is the source of the neutrons. These are the neutrons which come and then they get captured, and this is the source of the slow neutron process. And these are actually happening in stars which are quite high above the main sequence or in the Hertzsprung-Russell diagram, the so-called asymptotic giant branch or AGB stars, in which these processes are taking place, in which helium has also burning has also been completed. And then you can also have proton capture processes, which are the so-called, which lead to this P nuclei, 32 stable proton-rich nuclei between 74 selenium and 196 mercury. And these also happen along the proton drip-line side, proton-rich nuclei. And their processes generally happen in X-ray burst or nova or binary systems, when you actually have accretion of matter from one star to the companion neutron star, let us say, and it heats up the thing. As it heats up, in this production of this kind of P nuclei are produced. The S nuclei, basically they take care of almost half of the elements or isotopes above the iron or so. And then we also have neutron captures of the so-called rapid processes, which are happening primarily in the possible sites that are core collapse, supernovae, neutron star merger, etc. And this is happening all along the line of the neutron drip lines. And we actually know very little. And this is where the knowledge of nuclear physics, mass, lifetime, etc. comes very, very important. And this part we really do not know much about, and that is one of the challenges. So we had Big Bang nucleosynthesis, and we have this kind of very fast processes, R and P processes. This is a well-known plot, and that shows this path of the S process nuclei going like this. And the same thing is valley along which these nuclei are getting produced. And this is the plot for the R process nuclei. Similar plot I can show here, where R is there and the S, and then the RP or P process nuclei, as I talked about these binary processes in which these things are getting produced. So these are basically the sites. And now this is a nice plot which I have taken from Michael Weischer's lectures. And this is really a very beautiful plot in which you see the different masses and their abundances. As you know that we have hydrogen burning, helium burning, etc., carbon, oxygen, silicon, like that, and goes all the way up to iron, and these are all happening within the stars. Okay, and then this blue are the so-called R process nuclei, which are heavier masses, as you can see, and then the green are basically the P process, and this is a very nice plot that actually tells most of the knowledge that we have acquired so far. And of course, it's all started from this DB, Burbidge, Fowler, and Hoyle paper. So now we know what are the experimental challenges to us. The cross sections are, of course, extremely small cross sections. So we need high current and low energy accelerators. We need very low energy accelerators. As you know, inside the sun, the stars, the temperature is actually very low. So these are generally reactions happening at much below the Coulomb barrier. So the scenario is very different from what we are accustomed to in our normal nuclear physics or heavy and medium high energy or low energy, intermediate energy nuclear physics. So there is also sometimes we can do direct reactions, but they sometimes become very difficult, challenging problems. So need for indirect breakup reactions, or the so-called, we heard the surrogate reactions, in which Dr. Naik has actually made, is a pioneer in the country. And similarly, almost exactly in the same bracket, we get the Trojan horse kind of methods. So those are the so-called indirect methods. And then, so different methods are used for different reactions. And we also need to reduce the background. So there is a demand for underground measurements, okay? And then we also have to know that reactions can be done either by stable nucleus or by unstable nucleus. So one has to go to radioactive ion beam facilities. And another challenge is high purity targets, gas targets, etc. And of course, you need high efficiency detectors or array of detectors. So the accelerator, as I said, there would be either with stable beam or with radioactive ion beam. A stable beam accelerator is basically used for quiescent burning processes or big bang nucleosynthesis with high intensity and low background and with thick target. A typical, one of the most famous current facility is the LUNA, and where you can see I'm showing a very favorite reaction, 3 helium, that gives to 2p alpha, and you know this is the so-called PPCN reactions, which is consuming 4 protons to produce the alpha particles inside the stars. And you can see the 20 femtobarn or 1 count per month. That is the kind of challenge, and so one has to go deep down in the earth. And other similar facilities like in USA, Sanford Underground Research Facility, Notre Dame, and we heard yesterday a talk from a representative of Notre Dame, but not exactly on astrophysics. And the LENA, which is also a very important place of nuclear physics research in Duke University. However, now I will quickly go through some very nice pretty pictures basically, because I showed you about what is happening for quiescent process or these relatively smaller facilities with stable beam. But we can also have major facilities, which are the modern accelerator facilities, which were always working with stable beam or with over the last 30 years radioactive ion beams. They are also now making use of radioactive ion beams to do nuclear astrophysics research. One typical example is like this particular, I think this is possibly from, this is Michigan State. And like this reaction, 30 phosphor on deuteron, they're giving us to 31 sulfur like that. And you have very large scale detector facilities. So similarly, we have other facilities we know of, like the heavy ion storage ring at Heidelberg, or the upcoming high ISOL day at CERN. These are all major facilities, or will be major facilities of nuclear astrophysics, but using radioactive ion beams actually. Like another facility as Triumph, this Dragon facility, a very beautiful setup where you actually detect the gamma rays in this kind of an array, but also with the nuclei that is emitting it. But the idea is actually, for example, like these kind of reactions, which are of great importance for nuclear astrophysics. So the next plot shows similar facilities, and for measurements are basically now nuclear astrophysics. And so question is that what is going on in the Indian scenario? So we are just embarking upon it. Really never really had a very major dedicated facility for nuclear astrophysics, but now the community is growing and people are very interested. So one main facility, which is a small but very useful facility, is the ECR ion source at TIFR. So it is really not dedicated to nuclear astrophysics, but this is a very important facility for this kind of measurements. FOTIA facility at DRC has been there, which is also a very useful facility for this kind of measurements. The first and the most important fully dedicated facility that has now come up in the city of Calcutta in India is the FRENA facility as SINP, and I understand Professor Moitreyi Shah Sarkar in her talk will be covering a lot about this thing. So this is a picture of the FRENA facility, and this is a courtesy from Chinmoy Basu, a colleague from SINP. But I also mentioned the Pelletron and LINAC facility at TIFR and Pelletron LINAC facility at IUSC. You may ask that how this can be used for nuclear astrophysics. I have already mentioned about Trojan horse method, and that kind of reactions, if you want to do, you can do nuclear astrophysics. And also if you want to do, you can use these facilities. If you want to do industrial scattering experiments, you can also do in these facilities. So they complement each other. And this is the FRENA beam hall, and which is really ready and very encouraging to see this beautiful facility. So now the measurements that I will be just presenting, this is our fledgling field over the last few years and very recently. We have carried out few measurements which we could do wherever possible. And those measurements are basically, I have drawn one from capture reaction. One is the proton deuteron 3 helium gamma reaction. And this is of great importance for Big Bang nucleosynthesis. And another set of reactions, again, capture reactions, proton 10 boron, 7 lithium alpha, and these are two branches for this reaction, and proton 10 boron going to 11 carbon gamma reactions. These measurements have been carried out at the ECR facility in TIFR, the Triangle University Nuclear Lab at Duke University, and also our Peletron facility at the TIFR BRC facility in Bombay. And some inelastic measurements very recently, in the last 1.5 years, we have carried out using the Peletron facility again at TIFR at the nucleus to understand nuclear structure, but extensively the primary purpose is basically to do things whichever is useful for nuclear astrophysics in large. And but of course you have to have this also gives you information about nuclear structure and reaction. So let me quickly go through some of the facilities. Are rather simple things, but I'll just say the experiment, the detection facilities that we utilize or we have built up over the years. That is our very modest arsenal. And they're basically gamma ray detectors based upon scintillator detectors. So they are either large volume sodium iodide detectors or array of sodium iodide detectors, and large volume lanthanum bromide detectors or array of lanthanum bromide detector. These are basically our detectors which we use for our gamma ray measurements from low to high energy. So typical setups are like that. This is the TIFR facility, and this is a large array of sodium iodide detectors, and this is the array at IUSU was built a long time back. But these detectors, while so far have been primarily used for gamma ray measurements from heavy ion measurements, heavy ion induced reactions, but are actually the same. They can be used for the higher gamma rays from the capture reactions or the measurements at the nuclear astrophysics. So similarly, we have, so this is some of the typical pictures of the response of these detectors, and fitted with either GIANT or EGS kind of calculations. These are very important to know the response of such big detectors. This is the typical plot for this kind of different arrays of detectors. And then what we have built over the last, some years ago, and is very, very useful and powerful device is a detector that covers the 4-pi array. It's called 4-pi array, and what we made of conical, hexagonal, pentagon, and hexagonal sodium iodide detectors. And this detector is actually a very useful and very formidable device. And though it has primarily been used by for us to measure the fusion-fission kind of reactions, which we heard from Akhil in the last talk. And this is a typical setup. This is the same setup at TIFR, and this is the same setup now coupled with the gas field recoil separator HYRA at IUSC Delhi, so which is used to measure gamma rays and the multiplicity of the gamma rays, spin distributions, etc., in coincidence with their evaporation residue at the focal plane. So this is a very powerful device and very, very productive. However, what I want to emphasize upon the here in this talk, that this is a very, very powerful device for capture reaction gamma ray measurements in which will be used for nuclear astrophysics. It is a complete 4-pi array, and you can measure the gamma rays of the capture from the deepest ladder, and it is actually can be a very, very useful device. Other than the sodium iodide, we have also graduated to lanthanum bromide detectors, from very small size lanthanum bromides to very large volume lanthanum bromides that is available. And we have carried out a lot of characterizations and actually carried out nuclear physics measurements with detectors like large cylinder or large square bars and making arrays of them. And this is basically our arsenal. And you can see the measurement or calibrations for high energy gamma rays, either using scattering reactions, carbon, proton inelastic scattering of carbon, or measuring this monochromatic gamma rays to calibrate this detector, or by capture reactions to get high energy gamma rays of 22 MeV, etc. And you get a linear response, perfect linear response from 600 keV to 22 MeV, beyond 22 MeV with these detectors. So this is basically something about the detectors that we use. Now I would like to come to some of the physics results that we have got. As I said, I will talk about capture reaction and also about inelastic scattering. So let us start with the capture reaction. The first measurements that in the last few years we have completed, and I want to present to you, is about this proton deuteron. This is a very, very important and exciting reaction, because this reaction is important not only for nuclear astrophysics, but also for nuclear interaction per se, because it's a 3-body system. So for few body measurements is a very important thing. And as far this reaction is concerned, there are basically 3 scenarios. Okay, so the energy that, as for the experimentalist is concerned, the energy can vary from few keV all the way to tens of MeV or even 100 of MeV. It depends upon what exactly you are interested in. And we are interested in nuclear astrophysics as far this talk is concerned. So I can say in astrophysics context, there are basically three sites where this PD3 helium happens. One is the Big Bang nucleosynthesis, or we can have inside very low at Big Bang nucleosynthesis temperature is rather high, 10 to the power 9 keV, or we can have it inside the very small stars or protostars at 10 to the power 6, or in sun-like stars. Okay, so all these processes eventually lead to the depletion of deuteron. As far as Big Bang nucleosynthesis is concerned, the D by H ratio, which roughly is something like 2.5 to 10 to the power -5, but exactly also there are a lot of doubts about that, is a very important number, and it actually connects cosmologists, the astrophysicists, and the nuclear physicists. And the important challenge is to get this number right from nuclear physics point of view, as well as from astrophysicists point of view, who do their measurements by looking at distant quasars, etc., radiations coming from these very pristine objects which are far, far away. And the measurements should match. So this is a very important thing. However, when you talk about very low energy part, there is not much scope to do anything, because the Luna people have really completed all the measurements from 22 keV down to 2.5 keV. So there is not much scope. This is completely done. So we felt that it is important that if we do and go to Big Bang nucleosynthesis, and you will see that very, very little data, surprisingly, is available in the Big Bang region, and that is one reason. And there is a suitable beam energy because energy is higher, so we can do it even with our existing facilities. And there is a lot of interesting calculations which make very nice predictions. So this is the reactions we are talking about. This is one of the very few reactions in the Big Bang scene. And in the Big Bang scenario, temperature is rather high, so cross-section is high, or we are somewhere around this region. So let us just say that this is what I wanted to say. This region, this is completely done by Luna and others, but this region over the years is completely barren. So it is important we fill up these things and do these measurements. So this was a very rather simple measurement. So this is done at the ECR facility. So the beam is actually coming somewhere from this direction, and this capture reaction is taking place. We did it at 3 different beam energies using a CD2 target, and this is the ECSO ion source, and these measurements were done, and we tried to find out the cross sections and also the astrophysical factor from them. But as you want to do it on an absolute scale, you have to measure the efficiency very correctly. As for the Q value is concerned, around 5.4 MeV. So all the gamma rays that you'll be capturing will be around 5.5, 5.6 MeV. So we tried to do the efficiency measurement. This was done at Duke University. So this is the experimental data, and you may not see the GN simulation above it, but we are actually directly shooting 5.5 MeV gamma ray on the detector, and we are measuring its response function, and you get this perfect linear thing. Actually, we went ahead and we actually measured it all the way up to 70 MeV or so. I show it here only up to 30 MeV. So this was actually the first time for such a big detector using monochromatic gamma rays directly. This response was measured. Several years later, after that, Italian friends did it also at the Subaru facility in Japan. So this is very important for the cross-section measurements. These are the spectra. You see this nice. This is the fastest the peaks and the fastest escape peaks, and this is the GN simulation above them. So from this, I will cut it short and go fast. And we actually measured the cross sections, and these are our data. These were the only data which was available till date, and we got these 3 points, which are our data of the cross sections, and from that we also got the astrophysical S factors. So this was kind of nice, and this is very important because I have already hinted that if I go to the Marcucci's paper, which was coming out exactly on the same time, just before these measurements, and they actually emphasize, and also in private discussions, that however for the BBN relevant energy range, the experimental situation is rather unclear, since the only available experimental data are quite in disagreement with the polynomial best fit of astrophysical S factor in this region. And this gives rise to uncertainty on the cross-sectional level of 6% to 10%. So basically, to cut a long story short, you really need to have many data point accurate measurements, and then try to also see that those values that we get are actually matching with the values with cosmologists who are getting these values also from this baryon density at that time, and the neutrino effective number, etc. So these are the calculations of Marcucci, and these two are our data points, and one is a little away from that, but it is still within the band produced by the fittings of Adelberger. So that is about PD. So I can summary here that cross sections and S factors are measured for 3 new beam energies in the Babian energy region, the measured values are in good agreements with the limited global data set, and 2 of the data points are definitely in very good agreement with the Maruti's calculation, which is an ab initio calculation, and measurements of more beam energies are actually being planned. So I will change gear and I will remain on the capture ground, but I will just make some, I'll present some data which were taken a little earlier, and these were measured at the Duke University. This is about the proton and boron reaction. The proton-10 boron is actually very important because this is happening through scalation reactions outside the stars also, and the proton-10 boron will make 11 carbon, which will again beta decay and will make 11 boron. So this will come back to 11 borons, and so this controls the ratio of the 10 boron, 11 boron in the universe. So but it decays by 2 channels. One is proton 10 boron alpha and 7 beryllium, and another reaction is proton 10 boron 11 carbon and the gamma reactions. So I'll just quickly give these results. So these are all experimental details, so we can avoid that part. The important thing is that this was done from 2 MeV to 6 MeV, very elaborate measurement in steps of 100 keV, because we know that there was a very large uncertainty of at proton energy of 1.2 MeV, and there was a big gap in the S factor from 2.6 to 3.5. And these were all things done in the 60s and not done after that. Jenkins' work was in 1964, probably. So these measurements were done, and you see this whole data set, and they were actually angular distributions were measured, and then they were integrated to get the cross sections. And I jumped to the cross section plot. So this was the only thing that was existing before that, these measurements by Jenkins, and our measurements went all the way from 2 MeV to 6 MeV. More or less in the same line, but there is some higher values for our data, around 16% or so, but this part was clearly completed and went into the natural data table. So now, so this is the S factors also. As you see, earlier measurements are huge error bars, and it was much less in these measurements. So the conclusion is that this was good agreement with previous measurements. A broad resonance kind structure was found somewhere here, and we identify the corresponding lines, and this is another one, and this is another one. So now I talk about the gamma ray because it's the second channel which also has to be measured to get the cross section. Now this is more challenging and interesting because it is the gamma ray decay, the proton 10 boron 11 carbon going to gamma rays. So you use gamma ray detectors. So basically there was very little data. 2 significant measurements. One is by Kuan in 70 and in later 83 by Michael Weischer. But the Kuan measure was the gamma ray measurements directly to the ground state. So they were losing a lot of cross sections, whereas Michael Weischer's measurements with array of gamma ray detectors, so it was actually much better than that. So basically for this kind of measurements, obviously you will need a large array of gamma detectors. And in modern times, if you were to do nuclear astrophysics measurements with this, either you will do like this, I showed you in the facility in the Dragon, like that, or you will do, a very large array of detector, or maybe something like that. I mean, so that we have gamma rays. But then we thought of a technique, which is a very poor man's technique, but will get the cross sections absolutely without any loss. And what is that? That the proton and carbon is fusing to make 11 proton and 10 boron, fusing to make 11 carbon, and the 11 carbon and emits all the gamma rays very quickly, comes down to the ground state, and then it decays. It is a lifetime of 20 minutes or so. And it emits a positron. The positron annihilates in the target, produces 2 511 keV gamma rays back to back. So we carried all our detectors from here to Duke University and tunnel. And this is a simple beam line setup. This is the target, beam is coming. Then you put your large square bars of detectors just very close proximity to the target, and you detect these 2 511 kVs in coincidence. And after efficiency corrections, you will get the total cross sections exactly. Like this is a 2 511 kV gamma rays which you detect. And then what you do is actually, it's a simple experiment. The 20 minutes is the lifetime, so you bombard for 3 lifetimes, around 1 hour or so, stop the beam within 2 minutes, restart the data acquisition, and you detect the decay of it, okay? And then you try to fit it, and then going through the simple mathematics, you can get the cross section exactly in terms of all these factors. So let us have a look at the result. This is the cross sections that we got in the log scale I'm showing, and this is again the cross sections, but now I juxtapose the Michael Weischer's data, which is somewhere here, and then I also show the data of Kuan, which is far below. But this is obvious because they were measuring only to the gamma ray, which is a direct decay to the ground state. Okay, so this was a nice result, and So this is a very powerful technique. So we wanted to go higher up in the energy, and very recently, last year, we have just did this measurement at TIFR, 10 boron, proton, 11 carbon, gamma. And again, you see now we are using 2 cylindrical lanthanum bromide detector. This is our scattering chamber. The beam is going in this direction. There's a beam dump right there. And then we have measured this, and this is a very preliminary result. So we are analyzing still this. So we want to get these cross sections at a much higher energy. So now I come to the last part of this, where I will talk of proton carbon 12 pp prime gamma reaction. You may ask that what is the connection with astrophysics. I will say that, and in fact you may even ask that why in 21st century I am doing pp prime gamma reaction. What is left to be learned? It turns out that still we have to learn a lot. First of all, nuclear structure. We all know carbon 12 is an enigma. This alpha cluster structure, while state, etc., etc. And the different excited state that we populate by this pp prime, we want to understand the nature of the states and the role of alpha particle clustering, role of influence of giant resonances from 13 nitrogen, etc. And actually we will see, as for pp prime gamma is concerned, there is very little data. So there is a lot of data on pp prime over the decades. And also, as for theory is concerned, from optical model calculations, we can see that if we have a microscopic kind of a calculation, then the lowest energy they have gone is up to 40 MeV, but lower energy where nuclear structure is very important, there is actually very little calculations and hardly any calculations reproduce these entire cross sections for all the different energy levels. So we did these measurements. And also, as for nuclear astrophysics is concerned, this kind of inelastic scattering is very important to tell us about the elemental abundance at different sites. Because we look for the characteristic gamma ray lines, 4 MeV, 15.1 MeV, etc., look at their ratios, and from that we can get an idea about the elemental abundance. Like, for example, the satellite-based gamma ray astronomy measurements with this kind of facilities, RESI and Integral, they observe prominent nuclear lines, with good statistics long back. So it is interesting to actually do these measurements. So we actually try to get the cross sections from pp prime gamma from this state, and 9.64, 12.7, and 15.1. This is the Weyl state. And there was hardly any data, practically nothing from 9.64 MeV, and no knowledge about the branching ratio with the alpha versus gamma. So this is the simple experiment. The beam is coming from this direction. This is the scattering chamber, and we measured this angular distribution of the gamma rays with 2 arrays of, one is a single lanthanum bromide, and there is an array of lanthanum bromide detectors, and we measured these things. And this is the typical kind of spectrum that you can see, that you can get with the lanthanum bromide detectors. If you compare it with the old data, which we had all done with sodium iodide, you can make out the difference. So this is very important to have better quality data. And so we carried out, we tried to measure the cross sections for all the 4 states and angular distributions at different energies. They are almost the entire energy that Pelatron could cover, 8 to 22 MeV, and 6 angles, so adding up to 130 data points. So these are this typical figure. I quickly go through them. As the beam energy changes, you see the different lines are coming up. From 12.7, you get 15.1. As you go to very high energy, others are vanishing, cross sections are going down, and eventually you get only the 15.1 at 22 MeV. So this is exactly that what we got for the 15.1, and this is what was available in literature from old classic measurements of MISD, etc. And they went all this way up to this energy, but this is completely beyond our Pelatron energy, but we can get exactly the same pattern. So this is what we get for 4.4 MeV, the cross sections, for 9.64 MeV, and 12.7 and 15.1 MeV. And we also got for the first time the branching ratios for the gamma and the charged particle alpha decay for the 9.64 MeV. And we try to do some calculations. This is the results, and we are still doing it with collective model as well as microscopic models. And as you can see, if you do not consider, this is the data that we have reproduced from the calculations. Is a simple minded calculations optical model without any resonance. If you start adding them, you try to get a good reproduction. Like the green plot, this is all the data for pp prime, and you really do not take care of the resonances. Only you add it, you can reproduce the data. The same thing for 9.64 MeV. However, the challenge is really 12.7 and 15.1. And the 15.1, so far we have not been able to. Actually, there is no theoretical results that actually produce this 15.1, quite enigmatic. So we are actually still working on it, and hopefully we'll be able to resolve this issue. So if I summarize, so we have carried out exhaustive measurements of PP prime gamma from 8 to 22 MeV, and the cross sections of 9.64 MeV state PP prime gamma was reported for, we have reported first time. Branching ratio also for the first time, and rigorous optical model calculations have been done, and we are still working on it. And it is found to be very difficult to reproduce the 15.1 MeV state. And then very recently, last year, we carried out forward these measurements from carbon. We are going to oxygen and the cluster kind of nucleus. And we did these measurements at TIFR also with lanthanum bromide detector and also an array of sodium iodide detectors. And this is very preliminary, and this is some of the data. And this is just very preliminary, and we are working on it. So that brings me to the end of the talk. And I just show my collaborators, the younger colleagues particularly, who at Duke work with me, Adam Kafkarku, and Mona Lisa Devar, who got her thesis from one of the part of this work, Virendra Ranga and Shikha Panwar, and other colleagues from TIFR, IIT Roorkee, and Tunnel. So thank you very much. We have been talking about nuclear astrophysics, but we should not forget that last year the world celebrated the 150 years of the periodic table, and you cannot think of the subject of nuclear astrophysics without periodic table. And here is Professor Mendeleev by the banks of the river Dubna. So I once again take this opportunity to wish a good friend, Dr. Basant Kumar Naik, a very happy years ahead in the next phase of his life. Thank you very much.
Thank you, Indranil, for your excellent talk. You have showed us the importance of nuclear astrophysics, as well as demonstrated that how one can work with nuclear physics problems using the available facilities at and doing the experiments on like PD, then P boron, P carbon, P16. So many experiments you have done using the present available facilities. So now this session is open for discussion. So I'll request the audience to unmute oneself and ask the question. Yeah, before somebody asks the question, maybe I'll ask one thing. You have what is the relation between that S factor and the branching ratio of the inelastic state, that the last study that you showed? Can you tell me?
No. Okay. No, the S factor is related to, of course, the cross sections. And the branching ratio was basically that these are either gamma emitting or gamma and alpha emitting.
Yes.
So by branching ratio, I meant the alpha gamma ratio.
So by measuring this branching ratio, how it will help us in astrophysical studies?
No.
Will it help or? I think here Indranil has been disconnected, looks like. Yes, Indranil. You are muted, I think. You unmute yourself, Indranil.
Threw me out actually, just like that. No, the purpose of the inelastic scattering was basically to get the cross section so that one can get the abundances of the elemental abundances, basically. But from nuclear structure point of view, actually this is either is alpha emitter or it is a gamma emitter. Like 4.4 is primarily gamma, 15.1 is primarily gamma, but is 9.6 and 2 are predominantly alpha emitters. So this branching ratio was not known, so that came into that analysis.
Can I ask one question there? That the excitation function for this carbon excited states, 4.4 and 9.64, they look very different.
Yes, but okay, let me just see. Can you see this? Yes, 9.6 different. This is what we get, and from within the existing energy that we covered, I'll go to that. That is true. It is different. It is not peaking and coming down. Yeah. So this is what it is, and yeah.
I'm not able to see that slide if you have.
I have.
You have to present now. Again, you have to take your cursor down.
Yeah, and that's what I'm doing. I don't know how it is. Should come now.
No, not yet. Yeah, yes.
I have shared it.
Yes, coming. It's taking time.
It's coming. Okay.
Yeah.
Is it coming?
Yes.
Yeah. It has
Now
just
full
started
view.
coming.
Make full view.
Yeah.
Make full view.
Yeah, actually, this monotonic kind of increase for 9.64, whereas the lower two, the one at 4.4 and 12.7, they have a different behavior.
They have a different.
I was just wondering, you have any explanation for a?
Not exactly, but this part matches with the previous measurements. But this intrigue does also. Maybe one is to just go to higher energies. Because 9.64 is, yes, it is climbing. I agree with you. Hello?
Yes, yeah. Any other questions? You can take other questions.
Yeah, sure.
Is there any question on YouTube?
Can I ask a question?
Yogesh Gupta has question.
Yeah.
Can you?
Yes, Yogesh.
Yeah. Can you read that question?
Prepare 10 boron target in TI4 lab with case using what technique?
No, could you transmit the question? I didn't hear. 10 boron target. What was that?
Again.
Did you prepare 10 boron target in TI4 lab?
No.
Using what technique?
No, these thicknesses are given. The 10 borons were measured at the Duke facility, and yes, one was measured at the TI. For one, we just evaporated boron on this and on a tantalum backing. The Duke University measurements were measured their target lab, and the recent measurement last year it was made in TIFR by one of our colleagues in the target lab. Does it answer your question?
Okay, I think it's fine.
Yogesh? Yeah.
No, Yogesh is on YouTube, so yeah, Prakash has a question.
Okay.
Yeah.
Prakash?
Yes, sir. In this boron and P alpha reaction, whatever the beautifully you explain many resonances are, but high energy part you compare with the experimental data which is available, but low energy you see beautiful resonance. Is there any support in the hello? Is there any theoretical support? Let's say cluster model or ab initio calculation which supports this measurement. Then beautiful structure you have.
This is a good question, and let me just go to the proton 10 boron. Now this is a good question. Okay, the next one.
Yeah, this one. Yeah.
Yeah. So this will be. I do not know offhand these capture calculations, but there are different people are doing. Proton deuteron, we know of very proper calculations. Proton 10 boron, nothing is coming. At that time, we were really interested in the cross sections at that point. But full-fledged theory calculations for this proton 10 boron, I will definitely check and I will get back to you. Very proper advanced capture calculations, it's not coming to my mind right now. I do not know. I will definitely get back to you with this answer. Yeah, because this is a very important issue actually in the capture calculations, and in the PD and others, Viviani, this group capture calculations they are doing. Some persons in India also do, but I think proton 10 boron doesn't come to my mind at this stage. The theory.
Okay. Yeah.
Any other question? If not, then let us thank the speaker once again.
Thank you so much from my side also.
Yeah. So this brings us to the end of today's webinar session. So thank you all the participants and all the speakers of today, Professor Baldir Guimares, Akhil Jingan, and Indralin Majumdar. Thank you and good night.
Thank you. Bye bye.
Bye.
Okay, bye bye, Shatranjan.
Okay, bye.
Bye
So
bye.
people can leave the meeting now.
Yeah.
हाँ